if we start off with, we're going to talk about something known as a light clock. Okay, so let's imagine we have this handy-dandy spaceship here, and this spaceship has a light clock on it. So let's imagine over on this side right here, it's got a source of light. Okay, see that nice little light right there? And this light goes up here to a mirror. Okay? And by the way, this is in the book, and the drawing is exactly right there. So I'm just going to walk you through the derivation. So with this light clock, a light pulse goes poof on this side, and then it shoots, and it makes a nice sound, there and back. And we're going to call this the width of the spaceship. Okay? That's the width of the spaceship. Now, would we agree that that distance that it goes there and back would be 2w, right? The complete distance. And that the time would be t. We're going to call this t of the ship. Now, let me see if I can write ship correctly. It's embarrassing. So we have t of the ship for it to go there and back. Does that make sense? Would you agree the time for it to get up to the mirror would be 1/2 t of the ship? We agree with that. Well, also, since speed equals distance divided by time, and the distance would be speed times time. We're all good so far? Mm-hmm. Well, what's the speed of this thing going back and forth? It's the speed of light, which we're going to use c. Well, let's talk about just w here. If we're talking about just the width of the ship, how much speed is it? C, and the time is? 1/2 t of the ship. Okay, this is one of the things that we need. Okay? We good so far?
Yes.
Well, now, let's imagine, though, that this clock here, we now have an earthbound observer, or a person that's at rest, and the ship is moving with relativistic speeds. So now, instead, it looks like this. And I'm just going to have to do this. Here's the light flash. And it's going to be easier for me to draw it this way. That's supposed to be a right triangle. It's good enough. It's not exactly right. Too bad. So over here, we have our spaceship. Right? And then at this point, I should not be so high, but that's fine. Oh well. That's just making it worse.
Just put the little box. That makes everything a right triangle.
Okay, this is supposed to be the ship here when the light gets to that spot, right? And then now the ship is over here. Okay, so the ship has moved this far. Now, we could call this entire distance that it travels, we could call that the distance that the ship moves. But we're really going to be interested in this right triangle that we have here. So let's look at these parts of the right triangle. Just to make this easy, I'm going to call this, I need a better pen. These are just not working well. So I'm going to call this H, okay, for the hypotenuse. We're going to call this the W that we've already found, right? Didn't we find W? And we're going to call this half of that distance, I'm going to call it X. Actually, let me do this and make this really easy to see.
So we know the height?
What's that?
Do we know the height?
It's not height, it's a hypotenuse.
Or sorry. So
We're going to find that in a second.
Okay.
Trust me, I will get there. That's a little easier to see now, right? The HW and the X? All right. Well, this distance from here to here, we've got the velocity, we need to have a new time. The time it takes for the light to go poof, poof, and the time for the ship to go that far in my reference frame. I'm sitting over here, watching this ship fly by at a velocity of v. Well, if this distance is going to be v times t, and notice it does not have an s on it, does it, for the ship? That's my time. That's not the ship's time. Do we agree? Well, would we agree that x equals 1/2 vt? Half the time of the entire time? Well, then also, what about this? Isn't this going to be 1/2 t as well? It takes t to get there and 1/2 t to get there. But if this is light going this direction, then h will equal 1/2 ct. Full time, and notice that's a different t, isn't it? So that full distance, it's going to go t. So the time for it to get to the mirror is going to be half of that. And here, the distance for it to move, we're talking about the velocity of the ship, but this is light, and light has a very specific velocity, doesn't it? We all good so far?
So
All right.
the top t is 1/2 ts, right?
Yep. Now we're going to use this right triangle, and we're going to put it all together. Because we know that h squared equals w squared plus x squared. Pythagorean theorem, yes?
Yes.
We all good on that? Simple enough. Well then, we can say h squared is this 1/2 ct, so I'm going to put that in. And the w is this one, which is 1/2 ct of the ship squared. And this one is 1/2 vt squared.
Wait, don't you have to square the whole thing, not just the t?
Oh, yeah, thank you. Yeah, good job. Yeah, are we all good? I'm going to switch to the red because it seems to be showing up better on this thing today. Now, would you agree, Charlie, that this is going to be 1/4, 1/4, and 1/4 when you square them?
Yes.
They're going to disappear, aren't they?
Yes.
So now I'm going to get c squared t squared equals c squared ts squared plus v squared t squared. We in agreement with that so far? I would like to get these t's together. So I'm going to take this, and I'm going to do this. I'm going to move these over here. So I get c squared t squared minus v squared t squared. We good so far? I'm going to take the t out. Good so far still? I'm going to divide by this on the other side. Can you guys see this still? Still on?
You got like 6 inches that way.
Okay, then turn it this way a little bit. Garrett, can you do that real quickly? Just turn, because it swings on the top.
This way?
There you go. Is this good?
Mm-hmm.
Okay. So now, we're going to take this and we're going to divide by this c squared minus v squared, and we get t squared equals c squared ts squared. This is where we have to be real careful. That's the worst look at the t there. Over c squared minus v squared. We're good so far.
TS squared, right?
TS, thank you. Now here's the weird one. Here's the one that took me a little while to see. We got to get that c squared to the bottom. We want to get ts on the top by itself. So what I'm going to do is I'm going to do this. I'm going to multiply by the same thing on the top and the bottom. So you'd agree I can do that, right? As long as I do the same on the top and the bottom. And that now gives me all in agreement? Yes or no?
Yes.
And now I'm going to take the square root of both sides.
It shouldn't be TF squared anymore.
Oh, that's right. Yeah, that's done. Thank you. Audience participation. Correcting Murray all the time. So now, let's take a look at this and let's make sense out of it. Okay? If v is very, 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 very small, this is basically equal to 0, and these two times are the same, because the square root of 1 is 1. But as this gets to be bigger, an appreciable portion of the speed of light, then this is now less than 1, isn't it? And the square root of less than 1 is even more less than 1, isn't it?
Yes.
And a number divided by a decimal gives you a bigger number. 1 divided by 0.25 is 4. Therefore, t is greater than ts. Yeah. So, drop the mic. So now let's think about that. Now one of these is the proper time, isn't it? One of these is the proper time. Is it for the moving ship or is it for the person watching? What do you remember?
Ship.
The ship is the proper time because they only need 1 clock. So we're going to change this to a couple of different things. It depends on the person. You could do that for proper time. I think Tipler uses that. I've seen this from John Coley, and I've seen this, it's really a delta for night. Which one do you use? Who you working with, right? So just wait till your professor gives. It's important though that you know this is it, and then when you're actually working, get a cheat sheet and find out what the book says and write your definitions and just keep that cheat sheet with you the whole time. Okay? That make sense? But what we just did, now here's where I want to get really weird, okay? You might say, oh, well it seems like for the ship, the time is less. There's no seems like at all. It is true that for the moving object, the time is less. It does not seem to be less. It is actually less. If you were to do this trip, right, for this person down here, if they started there on the clock, over here, maybe they're here on their clock. But for the person on the ship, it starts like that, and when it gets back down, maybe it's only there. The amount of time it took for that light to get there and back was less for the ship than it was for the person watching the ship move. Now, some people say moving clocks move slower. And that's the point of that. Or you also saw in the movie, whatever that was, the one where we went to the other galaxy or whatever it was, where the guy was on the ground and his clock was moving faster. And the person up above, his clock was not moving as fast.
But that's because of time dilation.
That's what this is called, time dilation. And dilation, if you think about, when you dilate your eyes, think about this. When you dilate your eye gets bigger, right? Well, likewise over here, the amount of time seems to slow down. Okay, it's dilated. Okay, each second seems like more time.
It's weird.
Now, we can go one more step with this, okay? So, given that answer over here, I'm going to have to erase some of this to be able to do the next one, and Gary, if you'll make sure that they can see this.
Yeah, that's time dilation.
All right, well, let's imagine that we have a person going between 2 planets again. So, we start at the Earth, and we go to Saturn. Okay, there you go. And this distance from there to there, what's going to be the proper length? Is it going to be the spaceship moving, or is it going to be the person on the Earth watching? So the person on the Earth, this will be the proper time. And again, the proper length, sorry. And different books use different things. I think he uses, let me just double check, I think he uses a little L. It doesn't really matter what we do here to be absolutely sure. Proper length, L. So he uses this to be the proper length. Okay? And then the distance for the spaceship will be L. Okay? That's the proper length, and that's L. Well, remember that for the ship, for the person on the Earth, for the Earth reference frame, the ship is moving with a velocity of v. But if you're on the ship, the Earth is moving past you with a velocity of, I keep going towards the ball, sorry, that's bad acting, with negative v. Would you agree with that, yes?
Yes.
Okay? Well, what does that mean over here? Well, if we have the same velocity, okay? This is one where I haven't practiced it, but, you know, let's try it. So if we say, I'm gonna get myself into trouble, I think. Oh, well. So if the velocity is the same, okay, the velocity equals the velocity, we'll do that. Well, let's say that this is the Earth, and this is the ship. On the Earth, it's going to be L over, which time is it? Is it T or T proper?
T.
This is T, and this will be L over T proper. Do you agree with that? Okay, let's go ahead and put in what we know for this time, because this is now actually going to be T proper. Agree with that? Yes?
Yes.
Yeah.
Okay, so we're not going to put that in. Let me see, how much room do I have? Can you see, can they see me over here or not? Okay, so now we're going to have for L divided by T, which is going to be T proper over this thing, and we're going to actually, this is going to end up being an expression that we're going to use a lot. So we're going to actually call that something else in a bit. Over L over T proper. Oh, what do you notice cancels on both sides? T proper cancels on both sides. And I can, you know, so we're just going to get rid of that. And this is going to multiply, let's multiply by the reciprocal, yes? Okay, so we're going to have times L. Oh, that worked easier than I thought it did. So, here's my proper length. This is where I have to actually do this. This is the Earth, right? And this is the ship. Yes? Which one is bigger? The proper length or the ship? Because isn't this less than 1?
Yes.
Right? So this is smaller than this, right? Because it's this number multiplied by something less than 1.
Yes.
Therefore, L, let me see, let's do this. This is bigger, yes?
Yes.
L is bigger than L. Do we agree with that, yes or no? And I'm gonna do this just so that we can see this, I think, very, very clearly. This is Earth, and this is ship. Yes, do we see that? Earth and ship?
Yes.
And this is going to be Earth and ship. Notice, for the ship, not only is the time less, but the length is less. So for the ship thinks that the distance to Saturn is less distance. But it also takes less time.
I understand why you did the proof and everything, but couldn't you just also say for the first proportion you did there, since
Yeah.
they're equal?
Now again, Knight does this with something else. He uses what's called the Galilean, or the Lorentz transformations, which we will get to, which are really kind of the meat of this topic. But I wanted to do this in another way, just to make it simple. Okay, and we actually need this expression. This is one of the expressions that we're going to use for what's known as length contraction. Now, think about this again. Now that we've got this idea, remember all of these little things that we talked about the basics? Now, we've got this ship going between the Earth and to Saturn. According to the ship, the amount of time it takes for the ship to get to Saturn, for the ship, the amount of time is less. The person on the Earth says, oh, it takes you this much time. But the person on the ship says, no, it didn't. It took less time than that. But what does the person on the ship think about the distance?
Less distance.
It's less distance as well. Well, what about the ship as it passes the Earth? As the ship passes the Earth, the person on the ship says, oh, my length is 100 meters, whatever it is, right? But the person on the Earth sees the ship passing and says that the ship is
Longer.
shorter.
Shorter.
in the person on the ship, their length is the proper length, isn't it?
Yes.
This would be the proper length,
Mm.
which is greater than for the moving object. Because remember, now that he's on the ship, he's like he's on the earth. My ship is the correct reference frame. So I have the proper length. And the earth moving, the earth actually looks to be shrunk.
Because we're doing this whole thing from an outside observer.
No, you need to take it from both observers.
Well, the way you just changed it, but like all the derivations you just did, it's from.
Well, again, this is what you have to do. In this case, we went earth ship, right? Okay, and right now, all the stuff that we're looking at here, this is actually the trip to Saturn. But now if you want to talk about the length of the ship, now we got to look at this very close. So now let's change this and let's say this is the proper. Okay? And in this case, the proper one is moving or not moving. This is not moving, right? And this is moving. Over here, which one's moving?
Earth.
This one's moving. And this is, that's the proper, isn't it? See, that's where it gets a little weird, isn't it? Because, again, if you think about the person going from the Earth to Saturn, the person on the ship measures the proper time. But the person on the Earth measures the proper length. For the ship, moving, for the ship, not for Saturn, for the ship, who measures the proper length of the ship? The person on the ship. Now we want to talk about the proper time. Now we got to say what's moving and what are we measuring. If we want to measure the time for the ship to pass the Earth, who can use one clock? The person on the Earth can use one clock. The person on the ship has to have a person at that end of the ship and a person at this end of the ship go click, click. The person on the Earth can do it, oh, he's the front of the ship, ka-tunk. The back of the ship, ka-tunk. One clock. The person on the Earth would read the proper time for the ship passing the Earth.